There is a telescope so massive that it could swallow 30 football fields inside its bowl. It can hear a whisper from across the universe, a signal so faint that it would take your home Wi-Fi router 1 billion years to produce that much energy. Scientists are using it right now to hunt for alien civilizations, map the edges of the universe, and test theories that Albert Einstein came up with over 100 years ago. And the most unbelievable part? It was built inside a natural mountain valley in rural China, in a place so remote and so perfectly shaped by nature that it almost seems like the Earth was saving that spot for exactly this moment. This is FAST. And what you are about to find out is going to make the night sky look completely different to you. We are going to talk about the engineering that had never been tried before. The scientist who spent decades refusing to give up on an idea most people thought was impossible. And the moment a 30-ton metal pod was lifted into the sky with fingernail-width precision. But first, we need to understand why a telescope this size even needed to exist in the first place. If you are already loving this, smash that like button and hit subscribe, because this channel is just getting started, and you do not want to miss what comes next. Now, let us get into it. Why we needed a bigger telescope. When most people hear the word telescope, they picture a long tube pointed at the night sky, the kind you might find in a school science lab. That kind of telescope collects visible light, the same light your eyes use every day. It is useful, but it only shows you a tiny slice of what the universe is actually doing. Here is something wild. The universe is constantly sending out signals that human eyes can never see. Radio waves, for example, travel across billions of light years of empty space and arrive at Earth carrying information about things that happened long before our planet even existed. Dying stars, spinning cosmic objects, enormous clouds of gas between galaxies, and possibly, just possibly, signals from other intelligent life, all of it riding on invisible radio waves that pour down on us every single second of every single day. The problem is that these signals are almost unimaginably weak. By the time a radio wave from deep space reaches Earth, it has been traveling for so long and has spread out so much that it barely carries any energy at all. To detect it, you need a receiver that is absolutely enormous. The bigger the dish, the more signal you can collect. Think of it like collecting rainwater during a light drizzle. A small cup catches a few drops. A giant swimming pool catches everything. Scientists had known this for decades. They had been building bigger and bigger radio telescopes throughout the 1900s, each one more sensitive than the last. But even the best telescopes in the world were still missing things. Signals too faint to detect, objects too distant to see, and questions that simply could not be answered with the tools that existed. The universe was holding out on them, and the only way to get more answers was to build something dramatically, almost absurdly, bigger. That realization set the stage for the most ambitious telescope project in human history. But before we get into how it was built, it is worth taking a moment to understand exactly what this machine is hunting for. Because that is what makes the whole story so electric. What FAST is listening for. FAST was not built just to be big. It was built to answer questions that have been keeping astronomers up at night for generations. One of its most important missions is hunting for pulsars. A pulsar is what you get when a massive star, about 8 times the size of our sun, reaches the end of its life and explodes in a colossal blast. What remains is a tiny, incredibly dense ball of matter that spins at staggering speeds, sometimes thousands of rotations every single second. As it spins, it fires out a beam of radio waves that sweeps across the universe like the beam of a lighthouse. Every time that beam swings toward Earth, we detect a pulse, hence the name. What makes pulsars so valuable is that they spin with extraordinary regularity. They are, in a very real sense, the most accurate natural clocks in the known universe. By measuring the tiny variations in their timing signals, scientists can test predictions about gravity and the fabric of space that Albert Einstein first proposed over 100 years ago, predictions that are completely impossible to verify here on Earth or even anywhere within our own solar system. FAST can detect pulsars that previous telescopes could not even see, adding entirely new cosmic clocks to the catalog and handing scientists tools they have never had before. But pulsars, as fascinating as they are, might not even be the most thrilling thing FAST is searching for. FAST also has its receivers permanently tuned for signals from other intelligent civilizations. The search for extraterrestrial life has been ongoing for decades, but earlier telescopes simply were not sensitive enough to pick up a weak signal from a distant star system unless it was extraordinarily powerful. FAST changes that equation entirely. It can detect signals that would have been completely invisible to any instrument built before it. No one knows yet whether intelligent life exists anywhere else in the universe. But if it does, and if it is broadcasting any kind of radio signal into space, FAST is by far our best chance of being the ones to hear it first. Beyond pulsars and the search for alien signals, FAST is also mapping the structure of our own galaxy in stunning detail, studying the clouds of gas and dust drifting between stars, investigating how galaxies form and evolve across billions of years, and probing the very early universe in ways that were simply not possible before this telescope came online. Each one of those missions alone would justify everything that went into building FAST. Together, they paint a picture of a machine that could genuinely rewrite what humanity knows about its place in the cosmos. And to pull all of that off, the people behind FAST had to start with one very important number. The number that changes everything. 500 meters. That is the diameter of the FAST dish, 500 meters across. To put that in perspective, the average American football field, including end zones, is about 109 meters long. The FAST dish is wider than 4.5 of those laid end to end. Its reflective surface is made up of 4,450 individual panels, each one fitted with its own motor and control system. Together, they form a bowl so large that it would take you roughly 10 minutes just to walk from one side to the other. Before FAST, the largest radio telescope on Earth was the Arecibo Observatory in Puerto Rico. Arecibo had a dish 305 meters wide. It was considered one of the engineering wonders of the modern world, and scientists used it for decades to push the boundaries of what we knew about space. But FAST is nearly double the width of Arecibo, which gives it roughly 2.5 times the surface area, and makes it about 3 times more sensitive. That is not a small upgrade. That is the difference between hearing someone whisper in the next room and hearing them whisper from 3 blocks away, through a wall, in the middle of a thunderstorm. But here is the thing. Raw size alone does not tell the whole story. Building a rigid dish 500 meters wide is basically impossible. A structure that enormous would crack, warp, and buckle under its own weight before it ever had a chance to look at the sky. So the engineers behind FAST did not try to build a giant fixed bowl. They built something far cleverer, far more flexible, and far more impressive than anything that had been attempted before. What they came up with is the kind of solution that makes you wonder why no one thought of it sooner, and then realize that actually executing it was still one of the hardest things ever attempted in the history of engineering. The design that had never been tried. The FAST dish is not a fixed, solid structure. It is a living, moving surface. Instead of one rigid bowl, the dish is a flexible net strung together with 10,000 cables and anchored by 2,250 movable joints underneath. Each of those joints connects to a small motor that can push or pull its section of the dish upward or downward by very precise amounts. When the telescope wants to observe something in the sky, a computer sends commands to all those motors at the same time. Some panels rise, others lower, and within seconds, the entire surface reshapes itself into a perfect curved bowl aimed at exactly the right part of the sky. This shape is the ideal geometry for bouncing incoming radio waves toward a single collection point high above the dish. That collection point is a 30-ton metal pod called the focus cabin, suspended 140 meters above the dish, hanging in midair like a spider at the center of an enormous web. It houses all the equipment that actually receives the signals bouncing up from below. It hangs from just 6 cables, each one running up to a tall tower standing around the outer rim of the bowl. As the dish reshapes itself to track a signal, the focus cabin must move in perfect coordination, staying precisely aligned with the center of whatever curved shape the dish has formed. Using those 6 cables, engineers can guide that 30-ton cabin to any position and land it within 10 millimeters of a target point. 10 millimeters. That is roughly the width of your fingernail, at 140 meters in the air, using cables instead of rigid arms. That level of precision had never been achieved on a large radio telescope anywhere in the world before FAST. Of course, none of this engineering brilliance would mean anything if the telescope had been built in the wrong place. And finding the right location turned out to be just as important as the design itself. Radio signals from deep space are so faint that even ordinary human technology can drown them out completely. Mobile phones, power lines, the electrical systems inside nearby buildings, all of these things produce radio waves that interfere with what a telescope is trying to hear. To do serious science, you need a location as isolated from human-made noise as possible. You also need natural terrain shaped like a bowl, so the landscape supports the dish rather than working against it. In the Guizhou province of south-central China, scientists found exactly what they needed. Tucked deep into the mountains was a crater that had formed about 45 million years ago. It was naturally bowl-shaped, matching the rough geometry of the planned dish. The surrounding hills rose on all sides like a natural shield, blocking outside radio signals. The limestone ground beneath the crater allowed rainwater to drain away on its own, meaning the dish would never sit in standing water. And the nearest town was about 5 kilometers away, far enough to keep interference at manageable levels. It was, in almost every measurable way, the perfect location. The Earth had been holding that spot for 45 million years, and it turned out to be precisely what was needed. Roads were carved through steep mountain terrain to bring in construction equipment. Workers hauled metal, cables, and electronics through narrow paths that barely existed before the project started. A quiet zone was established around the telescope to protect it from interference, with the surrounding community working alongside planners every step of the way. Every challenge was enormous, but the man leading the charge had been preparing for exactly this moment for the better part of his life. The man who made it happen. Every extraordinary project has someone behind it who keeps the fire burning when everything gets difficult. For FAST, that person was Professor Nan Rendong. Nan was a Chinese astronomer who had spent his career thinking about where radio astronomy needed to go next. He first proposed the idea for FAST back in the 1990s, at a time when the technology to actually build it barely existed, and the engineering challenges were almost too long to list. The active surface had never been built at this scale. The cable-driven focus cabin was completely untested. There was no blueprint to follow, no earlier version of FAST to learn from, and no guarantee that the core ideas would survive contact with reality. Most people in the scientific community thought the project was too ambitious. Building something this new, this large, and this complex was the kind of thing that sounded inspiring in a conference room and impossible everywhere else. But Nan kept going. He served as both the chief scientist and the chief engineer on the project, which meant he was responsible for the big vision and the everyday decisions at the same time. He led a team that had to invent solutions to problems that had never existed before. Every major innovation in FAST, from the 10,000 cable net beneath the dish to the precision controls guiding the focus cabin, was designed from scratch by people working at the absolute edge of what was technically possible. Construction officially broke ground in March of 2011. For the next several years, the mountain valley in Guizhou was a massive construction site filled with workers, cranes, and hundreds of tons of steel and cable. Progress was slow, complicated, and full of moments where something unexpected forced the team to stop and completely rethink their approach. At one point, just days before the telescope's first test run, engineers discovered that the voltage reading from one of the 6 cable towers was behaving strangely, not catastrophically wrong, but wrong enough that it could not be ignored. A problem like that, discovered that late in the process, had the potential to set everything back significantly. The team diagnosed it quickly, corrected it, and moved forward without losing momentum. Then, in July of 2016, 5.5 years after that first shovel broke ground, the final panel was lowered into place by a local worker who had grown up in the very mountains surrounding the site. The dish was complete, but there was still one last challenge standing between the team and a fully working telescope, and it was the kind of challenge where a single mistake could undo years of work in an instant. The lift that could not fail. With all 4,450 panels locked into position, one final task remained. The focus cabin, that 30-ton pod the entire telescope depends on, had to be lifted 140 meters into the air and suspended above the dish using nothing but those 6 cables. This was not a simple crane operation. All 6 cables had to carry exactly the right amount of tension from the very first moment of the lift. If the load was distributed unevenly at the start, the imbalance could put dangerous stress on the cables or the towers, and at that stage of the project, causing damage to any part of the system was simply not an option. Years of work were riding on this single operation going exactly right. The team had practiced the lift extensively using a lightweight model, running through every step of the procedure until it was second nature. But a lightweight model is never the same as 30 tons of real equipment, and everyone on site understood exactly what was at stake. Before the lift could begin, engineer Yu Ruian, who had spent months working on the cabin's internal mechanics and knew its systems better than almost anyone, personally climbed up to each of the 6 cable towers to inspect the setup herself. She checked every cable, verified every tension reading, and walked through every detail until she was fully satisfied that nothing had been missed. It took about 10 days to complete all the preparations to her standard. Then the signal was given. The cabin rose slowly above the dish, guided by the cables, climbing steadily toward its position 140 meters above the bowl below. The towers held, the cables held. The precision control system worked exactly as it had been designed to work. When the cabin reached its designated point in the air, it settled into position within 10 millimeters of the target. 10 millimeters. After 5.5 years of construction, after thousands of design decisions made from scratch, after roads carved through mountains and 10,000 cables laid by hand, after a team of people spent the better part of a decade turning an idea that most said was impossible into something real and functioning, The whole thing came together with the width of a fingernail to spare. The telescope was alive, and somewhere out there, across billions of light years of space, the universe had no idea what was coming. If this blew your mind even a little, hit that like button, subscribe, and turn on notifications so you never miss a video. It genuinely helps more than you know. And here is the question I want to leave you with. If FAST picks up a signal one day that scientists cannot explain, a repeating pattern from a distant star system that looks nothing like anything natural, what do you think we should do next? Tell the whole world immediately, or study it quietly first? Drop your answer in the comments. I want to know where you stand.